This video is entitled Trig Identities Part 14, and it is a replacement for a video I did also entitled Trig Identities Part 14. Now, why am I replacing one of my videos? Because it contains such an egregious error that I didn't want you guys to learn it. Okay, now, I'm going to dedicate this video to Professor Rob Bob and your math girl. And the reason I'm going to do this is because I feel they're better trig teachers than some of the ones that I've run into recently. Sometimes a trig teacher will stand there and say, well, the reason things are the way they are is because I said so, or that it's just in that book. Well, I don't care whether you say so or whether it's in that modern day textbook or not. That's not a good explanation. So, these two teachers have challenged me to try to find a much better explanation for what I'm trying to say. Now, what seems to be the problem? Okay, let me go into this. What we're trying to do is we are trying to prove that the cosine of A equals the cosine of negative A. Like that. Now you say, well, that doesn't seem to be much of a problem. Oh, but it is. Okay, here's how this works. Do you remember in Trig Identities Part 13, for those of you who actually watched it, I said that if you have a 45-degree angle in quadrant 1 and a negative 45-degree angle in quadrant 3, that the cosine of A and the cosine of negative A were going to be equal. No problem. Now here's the part where trig teachers start to squirm. Well, what if you have a 45-degree angle in quadrant 2 and a negative 45-degree angle in quadrant 3? Well, again, the cosine of A equals the cosine of negative A. Now already they're starting to squirm because they say, well, there's no 45-degree angle in quadrant 2 and there's no 45-degree angle in quadrant 3. Well, let me tell you how they reasoned that out. My students, that is. They say, well, didn't you teach us about supplementary angles? Yes, I did, in Euclid's Elements. Well, didn't you teach us about vertical angles in Euclid's Elements? Yes, I did. Here's where the problem comes in. Okay, well, I said, well, if you have supplementary angles, okay, and you have a 45-degree angle, then the other angle, which is 100 and some odd degrees, and I'm sure somebody will calculate. As a matter of fact, I'm going to leave that as a challenge. If this is 45 degrees, then the supplement of that would be 100 and what? You tell me in the comments below what the supplement of 45 degrees is. I want you to do that. That's your first challenge. We're not done challenging you yet. We're not done. Okay, so if this is 45 degrees and the supplement is 100 and some odd degrees, which now you're going to list down the comments below, then we can say, well, this negative 45 degrees has a supplement which is a negative 100 and some odd whatever, which you're going to leave in the comments below. That's right. So that's how we come up with this. Okay, let's play along a little bit. Now you say, well, what about these vertical angles? This is a negative 45 degrees, this is a positive 45 degrees, and that cosine of A does not equal that negative cosine of A. If we're using that kind of reasoning, you're absolutely right. But we're not going to use that kind of reasoning, because that's a shallow understanding and comprehension of Euclid's Elements. Now, in order to break all this, you have to go back to Euclid's Book 2, proposition number 12. What is Euclid Book 2, proposition number 12? Well, it's the law of cosines. That's what it is. Now, you also have to go back to Euclid Book 3, proposition number 20. What is Euclid Book 3, proposition number 20? Well, that's the law of sines. But we're not done yet. Nope. I'm now going to introduce you to Claudius Ptolemy. Who in the heck was Claudius Ptolemy? Well, he was a Greek mathematician who had Roman citizenship. That's why he's known as Claudius Ptolemy. The P, by the way, is silent. Okay. Now, what did Claudius Ptolemy come up with? He came up with something called the Table of Chords. Now, I'm going to leave a link down below to a page which is going to talk about Claudius Ptolemy and his Table of Chords. And specifically, I'm going to reference you guys to a spot which he shows a picture of a circle, and he talks about how he divided the diameter into 120 degrees and 360 degrees respectively. Now, and he's dividing it into parts, okay? And I want you to reference that down below, because that's going to explain the Table of Chords. Now, I don't completely understand, nor do I comprehend what all that means. But I'm sure your math gal and Professor Rob Bob will be more than willing to enlighten us on what they're saying. I know they're saying something very, very important, but I just don't know what it is. And if they don't enlighten us, I'll do my best to do it myself. But anyway, that's the first part of this explanation. Now, the next thing you have to remember is that Claudius Ptolemy and Euclid himself lived in a time where they didn't use negative numbers. Oops. So that meant all the angles were positive, not negative. So that kind of puts a kink into that vertical angles thing you were trying to say. Well, these are supplementary angles, these are vertical angles, so therefore, no. These two people lived in a time in which they did not use negative numbers in geometry. The only time negative numbers were used back then was when you were buying and selling things. If you wanted to figure out land acreage, well, there was no such thing as negative land acreage. It was all positive. When you were dividing the land, it was all positive. And that was farmland, from what we're talking about here. They were dividing up farmland. If you were talking about pyramid building, you didn't have negative pyramids. You had positive pyramids. Everything was measured in magnitudes. So now that you're starting to put all these pieces of information together, we have a couple more pieces we need to throw into the mix. Oh yes, we're going to get better. Now, as you know, in ancient times, they didn't have modern day GPS equipment. What they had was a very special star in the night sky. And as long as you could see this very special star, you could navigate your ship from wherever you came from to wherever you were going. Now, in my next question, I want you to name that star. Put the name of the star down here below. Okay? Now then, we're going to fill in the next piece of information. Alright. The sun rises from a particular part of the sky, and it sets in another part of the sky. From which part of the sky does the sun rise, and from which part of the sky does the sun set? This is very important. I want you to list those down here in the comments below. Now then, if you are facing that very special star, and you're watching the sun rise, which I wouldn't watch it directly, but if you're watching the sun rise from that one point in the sky and following all the way over to the other part of the sky, you can start seeing how angles went counterclockwise. Now this is in stark contrast to, you know that little compass we use periodically in my Euclid Elements videos? It has the pencil on one end and it has the little Sharpie thing on the other. Okay, now you know when we twist that, we twist it clockwise, but when you watch the sun go from one part of the sky to the other throughout the day, you'll see why angles are formed counterclockwise. Especially if you're staring at the part of the sky where that special star is. Are we starting to get the picture now? The Cartesian coordinate system was created long after Ptolemy and Euclid. Ptolemy and Euclid had already come up with a table of signs. Now I know that Ptolemy came up with a table of chords, but it was able to be translated into the table of sines. Euclid himself came up with the equation for sine and cosine. Now, all of this was done in positive numbers. Now, putting all these puzzle pieces together, you can begin to see why this is not going to work. Because this can't be 45 degrees and this can't be negative 45 degrees. Why? Because of Euclid Book 2, proposition number 12, otherwise known as the law of cosines, Euclid Book 3, proposition number 20, which is the law of sines, and because of Claudius Ptolemy and his table of chords. Now, there is another equation that I'm going to leave to you guys. I'm going to leave a second link down below, and it's about Euclidean angles, okay? And they're talking about how they're determined by the corresponding right triangle. And hopefully you guys can expand on what these people were saying so we can get a better idea of what they're talking about. So like I said, I'm going to leave a second link down below, and hopefully you guys can translate that out for us. If not, I'll do my best to translate it out myself. But hopefully your math gal and Professor Rob Bob can do that. Or maybe they can give it to their students, and maybe their students can translate this out, so we can have a better idea of what we're dealing with. So, based on Euclid Book 2, proposition number 12, Euclid Book 3, proposition number 20, based on Ptolemy's table of chords, and based on this Euclidean angle thing that we've got down below, not to mention the fact that all angles back then were positive, and if you look towards the special star and watch the sun rise from one direction and set in the other, you can begin to understand why none of this will work, and why the cosine of A equals the cosine of negative A. Alright. Now, hopefully in my next video, which will be Trig Identities Part 15, I can shed a little more light on all this stuff. I hope your math gal and Professor Rob Bob can also shed a little light on this stuff. Maybe their students can shed a little light on this stuff. Alright. I will tell you more in a future video. Stay tuned.